Okay. Now we're talking about a phenomenon of a domino on a meter stick. And as I tilt the meter stick, the domino stays there. It stays there until it doesn't. Okay. Makes sense? You know what's going on? Well, we did some discussion. People pretty much know that, you got gravity acting on the thing in this direction. Okay. You have a normal force. Might be able to demonstrate this. Let's see, no, that's not high enough. Wait a minute, this is still higher. Climb the lever. Okay, now I think maybe we can do a little bit of this. Okay, so still a little bit of a stretch. Let's do this. Okay, now if I bend this thing down and release it, what's the path of the domino going to look like? It's going to go straight up? Well, yeah, parabolic path here. You could analyze that parabola. Okay, it went up about that far, which is about 37.3 centimeters. And when it passed the meter stick again, it was 18.4 centimeters down the meter stick. Okay, or whatever your estimate you want to make. You could actually analyze that parabola. Figure out how fast the thing was going when it left the meter stick, for example. Okay, well, the point of that, though, was not parabola, the parabolic arc, not the uniformly accelerated motion in 2 dimensions, projectile motion thing. It was that the normal force was acting perpendicular to the meters, okay? Because the domino is itself bending the meter stick down a little bit, and the meter stick is reacting with a force in the same direction as the force we just saw. It made it go in this direction, okay? But of course, a much smaller force. So if we take the domino off, the meter stick doesn't snap back to its original length. It does in the probably micrometer range. Okay. All right, so what was it that was preventing this thing from sliding down? The friction, right? So we discussed that, and we came up with the idea that, yeah, okay, friction's acting down, normal force is acting here, and the frictional force is acting back up the incline, okay? So we want to draw a diagram of that. So what I asked people to do was make a dot and show me the 3 vectors that represent the 3 forces that we know are acting on that domino. Okay. Now a lot of people went ahead and drew the system, and the artwork was fantastic. Okay. But next to that, I want you to actually put a dot, and everybody did, and everybody got a good picture. So we have this. And I'll label this as weight equals mass times acceleration of gravity. And we haven't even introduced the whole concept of force and acceleration, but everybody pretty much knows it. And we'll build it up. Whether you know this or not, you can draw that graph, right? Okay, so that happens to be mass times acceleration of gravity, because if you take that mass and release it, it's going to accelerate downward with the acceleration of gravity. Okay, if there's nothing holding it back. So you know that that's got to be the force, but we haven't really talked about that. That makes it completely clear. Okay, we have a normal force. Now, if the slope is this way, then the normal force would be perpendicular. Maybe like this. Then there's a frictional force, which is along this. Now I'm going to go ahead and draw the direction didn't do a very good job of that, but there's the direction of the incline. So that now I know to put the frictional force here. I'll do that with a small f and an FRICT subscript, just to make sure we know it's a force of friction. But wouldn't want to do f sub little f. That would be kind of weird. Let's fill out the FRICT. All right. So I got those three forces. Now we notice that as I have the domino on the incline at the angle of the incline, it was stationary. That means these three forces are perfectly balanced. Okay. Now, what do you think the angle is between the weight vector and, well, I'm going to introduce this. Okay. I'm going to make this the x-axis, and this is the direction of the meter stick. And the y-axis will be the direction perpendicular to the direction of the meter stick. Here's the y-axis. What is the angle between the weight vector and the y-axis? Just estimate, what do you think it was with the actual meter stick? And don't worry about whether the picture is accurate or not. Don't use the picture as a basis. Remember what the meter stick looked like. And I demonstrated this 2 or 3 times at different angles, so you pick your angle. Tell me what angle you think it was. Or if you wish, what was the angle of the incline with horizontal? Let's do it that way. Okay. So what angle does the x-axis make with horizontal? Okay, everybody's estimated an angle. And if this is horizontal, then people are telling me that this angle here should be about 30 degrees or 50 degrees or 15 degrees or 18 degrees or whatever, okay? So we've got an angle here. I'm going to call that angle theta. Okay. Two of these vectors, the normal force and the frictional force, are in the direction of coordinate axes, right? So in terms of I and J, what's this? Normal force is what times the I vector plus what times the J vector. Frictional force is what times the I vector plus what times the J vector. Just using the symbols F sub n and F sub friction. What are those forces? What are the I and J components of each? Okay, well, the F sub n vector, capital N, the F sub n vector has 0 I component because there's no component in the X direction, right? Plus F sub n J, where F sub n doesn't have an arrow over it, and F sub n stands for the magnitude of the F sub n vector, does have an arrow over it. You know that. You know, we'll do that. Okay, standard, everybody uses this convention. So we can use just the letter F sub n or the symbol F sub n for the magnitude of the force. So obviously, what's your frictional force? Well, it has no J component. It's 0 J. It's little f friction times J. Okay. Now, what are the components of your weight vector? And here's your weight vector. Here's your y-axis, here's your x-axis. We can draw a projection line. Like so. And the components of the weight vector are this and this. Okay, well, what's this? Well, if this angle is theta, what's this angle? Hey, what's this angle? 90 degrees minus 90. Okay, well, we're going to use this. We don't have to worry about 90-degree minus thing. And we see that the magnitude of this vector here, just like the three sides of the triangle definitions of sine and cosine, is W sine theta. Okay. And the magnitude of this is W cosine theta. However, because of the fact that this thing's in the fourth quadrant, this is negative W cosine theta. And now it's a vector. Well, the vector then is W and I'm writing that down below. Think about what I'm doing. Okay. It's going to be W sine theta times the I vector, and then minus W cosine theta times the J vector. Makes sense? Go back to the triangle and you get this. And if you don't see that instantly, go back and do some more problems in chapter 2. Okay. Make sure you have all the vector stuff down real well. Okay. Because you're going to need it like crazy in the next couple of weeks. Okay. So that's one way to do it. So this would be negative W cosine theta times your J vector. And this would be W sine theta times your I vector. Getting to the crowd version, play with the theta someplace else. And of course, this angle here is theta. Okay, now, if the forces all add up to 0, then what can you say about the forces in the y direction? Well, the forces all have to add up to 0. If the forces add up to 0, that means you end up with 0i plus 0j. Okay, so the off the board with this stationary domino. Right. sum of the vector forces is the zero vector. It's not zero, it's the zero vector because these are vectors and they add up to a vector. And the zero vector, of course, is zero I plus zero J. That makes sense? Okay, well, this means then that F sub n plus F sub friction plus W equals zero I plus zero J, doesn't it? Now we have all three vectors now written out with their I and J components. So can you rewrite this equation using the I and J components of every vector? That's good. Rewrite. Fortunately, I didn't get the components very well. But anyhow, rewrite with all the I and J components. What do you get? You get an equation. Okay. And then the question is, can you solve that equation? Okay, so this is pretty simple now. All I ask you to do is write this out by substituting these expressions for these. Okay? And everybody that has had statics wrote out their statics equations instead of doing what I asked. Okay, which is okay. I mean, we're going to do it too in a minute. Okay, so it's perfectly valid and it's even actually in your text. But we want to make sure we understand totally the linear independence of these directions and everything else rather than just assume. All right, so well, Fn is just Fnj. We can leave out the zero I because that's just a zero vector, right? Okay, so you write Fnj plus F fric I, everything myself through, plus there's our equation. That's what I asked for. Okay. Now we solve this equation. The I components add up. So we have this I component, this I component, factor out the I and all that stuff. Final algebra. And then Fn minus W cosine theta J equals zero I plus zero J. This we have read that out. Okay. So now what does this tell you? This tells you the only way these vectors can be equal is to the coefficient of I here to equal the coefficient of I here. So coefficient of I here is this, coefficient of I here is 0, so they're equal. Coefficient of J is this, coefficient of J is 0, so this equals 0, right? Now I said solve, didn't exactly tell you what to solve for. Let's assume that you know the weight of the domino. Okay. That's that. Puts F in and F friction turns to W. Well, these are very easy equations to solve in terms of W and theta. What's that mean? That means that this equation tells you so F friction equals W sine theta. And then from that, you would conclude that the Becker friction is negative W sine theta times I, which makes perfectly good sense in terms of the diagram. It tells you that this force is equal and opposite to this one. That makes sense? If this is equal and opposite to this, because they got to end up to zero. There are only two forces in the x direction. One has to be opposite of the other. Now you could have seen that from the diagram and not even had to go to the equations and stuff, but add a couple more forces here in different directions, and you're going to want to go to the equations, right? And sometimes you can write the equations down directly from the picture. But you should understand in every case that what you're writing down is the sum of all the forces. The vector force is a zero vector, which is 0I plus 0J, if you're in 3 dimensions, plus 0K. Okay. So the formalism of this is as it is. Get this, which I said is obvious from the picture. And the other solution is also obvious from the picture. But again, writing everything out the way we have to do when things aren't as obvious. Fn minus W cosine theta equals 0. Fn equals W cosine theta. In the vector Fn, W cosine theta minus J theta. And again, that's obvious picture. You have negative W cosine theta J here, and you have Fn here. They're equal and opposite. Opposite of this is plus W cosine theta times J, and that's what Fn is. Okay. You want to have a clear picture, you want to have a clear diagram, you want to be able to do formal thing where you just do sum of F equals 0. Although your book is probably going to tell you that that reduces to fact that sum of your forces is 0 means if you add up all your fx i's and all your fxj's and for fyj's and all your fzk's, you're going to get 0 I plus 0 j plus 0 k, because that is the 0 vector. Now, I went into 3 dimensions just in case you need it. You probably don't need it much in the chapter we're doing, but it's really easy to just extend to 3 dimensions. Now, things get more complicated in 3 dimensions, but not always. Okay. It's just forces in 3 dimensions. You just add them 3 dimensions, get all the components. Okay. So this means that coefficient of I here, I can be factored out. You have I times the sum of fx equals I times 0, so sum of fx is 0. And same for y and z. Okay. Now that's where you start in statics. And it's okay, because it's pretty intuitive no matter how you do it. Okay, I don't have any objection to the way you did it in statics, but I wanted to show it this way. So it makes sense to everybody, even those who haven't had statics. Okay. And there's at least one person here that hasn't been, or 2 people, 3 people. No, 2 people. 3 people. Yeah, 3 people are here today. And probably for good reason. Recent disaster. Okay. We do have a disaster center set up in the middle of town. And they're all over Southwest Virginia and Eastern Kentucky. I don't know where else. Down in the Carolinas, it's terrible. The Damascus is under 5 or 6 feet of water. And that's receded somewhat. It's talking to people, but still bad. So, depending where people are, they might not be able to get here, but we'll have a video. Hopefully, everybody has internet. All right, so that's where we are. Well, those are your conditions. This is the condition, and these 3 things follow from this condition. Of course, this follows from these 3 things as well. Okay, so it's an if and only if this, if and only if this, if and only if this. Every statement there is equivalent. So it doesn't really matter which one you start with. Okay. Anytime an object is in equilibrium. Now, equilibrium means what? Okay. And let me just kind of pose this one so we'll discuss it briefly. Particle is a mass that doesn't rotate. Okay. You saw if we start our beam in rotation, that different masses at different points on the beam are going to have different velocities and different accelerations. That's complicated. Now, it's not too difficult to cut through the complication, which is a little bit of calculus. Okay. But we don't want that complication when we're just trying to understand forces and particles. Okay. So, particles of mass doesn't rotate. Equilibrium of a particle means acceleration is a 0 vector. Acceleration is a vector. So I write it as a vector. Okay. Now, a lot of times we're dealing in 1 dimension. you think the acceleration is just a hay with no arrow over the top of it. In 2 dimensions, as you know, from the chapter we've just completed, you better have an arrow over it and better think of it as a vector, right? Okay. Okay, well, now we have Newton's first law that I'm not going to write down. Your book has it written down better. It just says if something's moving at some velocity in a straight line, if it's in equilibrium, it's never going to change its direction or its speed. Okay? Because it's in equilibrium, its acceleration is 0. In order to change its direction, its velocity has to change. Right? In other words, those magnets at the end of that rotating beam keep changing direction. Okay? Acceleration 0 means acceleration is 0 unless there be forces. Okay? Like in the old maps, here there be monsters. Okay? Here there be no forces. Okay. Newton's second law. If you have a mass, whatever mass it is, anywhere. F net equals mass times acceleration. What do we mean by F net? It's the sum of all forces acting on the object, okay? Because of course, gravity had a component in the direction down the incline with that domino, right? But that domino wasn't accelerating down the incline because you have a force of friction. If you have a frictionless incline, the object will accelerate down the incline, okay? If you think that because the component of gravity in the direction down the incline was 0.2 of a Newton. No, 0.02 of a Newton. Okay? If the thing was accelerating due to that force down the incline, you'd be wrong because the frictional force is part of this force here. And so you can't just take whatever force you think is the most obvious force and say, well, that's equal to mass times acceleration. So we can take the acceleration, divide the force by the mass, and that's however we can find the acceleration by dividing the force by the mass, right? Well, you can't if you do use the net force, not if you just use whatever force you happen to be applying. Trying to move a refrigerator across the floor, okay? You're applying, maybe 60 or 70 pounds of force, maybe more if the thing's really sticky, right? Okay, then you're gonna accelerating the thing maybe. If you divide that 60 or 70 pounds of force by the mass of the refrigerator, and of course you better do that in a consistent system of units. talk about that in a minute. You're gonna be wrong because there's a frictional force that's resisting your motion. And you might just be moving at a constant velocity, okay? That makes sense? You gotta take all the forces into account, that's what F net means. Don't write F equals ma, write F net equals ma to keep reminding yourself of that, because it's a very common error for people to screw it up by just putting whatever force is most obvious in there and using it to calculate the acceleration, okay? So even if it says F equals ma, no, it's F net equals ma. F equals ma is something you should probably never even think about. Okay. It's a little simpler without the subscript, but you get into all kinds of confusion unless you're well aware of this. Okay. Now let's talk about the units. Okay. SI mass unit or kilograms. You have other units that are going to work pretty exclusively in SI units. And understanding we know how to convert to other forms of units, other systems. Okay. Acceleration units are meters per second squared. So force units the units of mass times acceleration are kilograms times meters per second squared. Net force is mass times acceleration. Then the units of net force are the units of mass multiplied by the units of acceleration. It's that simple. Now there's a word that we use for this. Kilogram meters per second, also called Newton. So if you see newtons, you know it means kilogram meters per second squared. What's the advantage to knowing that it means kilogram meters per second squared? If you have a complicated calculation, you want to check out all your dimensions. You want to do your dimensional analysis. You want to check out all the units. And all the units that we use in physics, at least all the units we use in this part of physics, you know, they're also amperes and stuff like that. We get into electricity and magnetism. But the units we use in just plain old mechanics all boil down to kilograms, meters, and seconds. These fundamental units that you read about at the very beginning of your text. Okay. You might want to just go back and read that again. Take 5 minutes to read that again, just to kind of get that scheme in your mind. But I'll keep reminding you. So one way or another, I hope you remember. Okay. So there we have it. Okay. So let's say that we have a domino on an incline. And the angle of the incline is theta. So that sum of your x forces is this. As we saw before, mg cosine theta minus the force of friction. Okay. Mass is 0.02 kilograms. Force of friction is less or equal to mu times mg. Equilibrium occurs if the sum of forces, x forces is 0. So mg cosine theta minus force of friction, which is now mu times mg, equals 0. Well, that's not necessarily true. Mu is going to be a number for that domino. I think it's around 0.3. So what you have here is mg cosine theta minus 0.3 mg equal to 0. Well, that's okay as long as theta is small enough. And this is x force. I just kind of automatically divide the cosine of x force. It's mg sine theta. What I was about to say just wasn't going to work. Actually, I had to stop and think about that for a second. Okay, this is sine theta. Then you go back and have sine theta there. Oh, yes. Okay, so we have this equation. Okay, so now if theta is a small angle, sine theta is small, right? Sine of 0 is 0. Okay, then this theta starts increasing. Sine of theta increases. At some point, theta will increase to where sine of theta equals mu. Okay. I wrote something here that I should have done. This should be the force of friction. One thing I'm trying to do here is convince you the force of friction is not always equal to mu times mg. It's less than or equal to mu times mg. Have equilibrium if the sine of theta equals, well, mg sine theta equals a force of friction. Force of friction can't be bigger than mu mg. So there's a limiting angle that you can find by setting mg sine theta equal to mu mg and solving for theta. That makes sense? The force of friction, well, let's just make sense out of it. Okay. Imagine that this was a frictionless incline, that any little tilt would cause the domino to slide down, right? So if I want the domino to hold still and I have to exert that force myself, then I don't have to exert much force at this angle. At this angle, I've got to exert more force. At this angle, I've got to exert more force. Again, assume that this is frictionless. So the force I've got to exert to hold this back keeps increasing. Well, now if we do have friction, it's friction. It's holding it back, holding it back, holding it back, holding it back, holding it back until there's no hold back anymore. Okay. The equation says mg sine theta has to equal the force of friction to hold it in equilibrium, but the force of friction can't be bigger than this. So if you set this equal to this, you can solve for the angle. Because mg would be on both sides. And let me just write it out. And the angle is the inverse sine of the coefficient of friction. And that's a limiting angle beyond which you're going to have things sliding. Also, when things slides, the coefficient of friction decreases. You have static friction and kinetic friction. Static friction holds it there, but as soon as it slides, you notice that as soon as we hit that one point, things started accelerating down the incline. Okay? It didn't go down at a constant velocity, it started accelerating because force of friction decreased to the point where your mg sine theta minus force of friction is suddenly some finite number greater than zero. All right. Now, if you're taking statics, you probably understand that. If you're not, I'm going to have to, digest that a little bit. So we're not going to assume that everybody knows statics. I don't know about the 3 people that aren't here. I don't know how many of them are in statics, but we got to teach the course without assuming statics.